Okay, can you see my screen now?
Yes, sir.
Okay. So let me recall what we have been doing. We uh, we were studying linear functionals. So we know that if we have a vector space, then we can talk about its dual space. The dual space is just the space of functionals, all linear functionals. And then we saw that if we have a like if we fix a basis for the vector space, then we can always find its dual basis. And then the converse is also true. That means if we have a basis for the dual space, then we can always find a basis for the vector space such that for which the given basis is the dual. So the converse was answered by introducing the double dual. Okay, so double dual of the vector space. All right, and then we introduce the annihilator of a set, and we saw some properties also and how to compute annihilator of a given set. And if we are given some functionals, then we can also compute find the subspace which is annihilated by the given functional. So these things we saw. So like we introduce double annihilator. The same way we can also talk about we introduce double dual. The same way we can also talk about double annihilator. So it's like we have a we have a vector space and we have a subset of it. Then we can talk about its annihilator. So annihilator would be a subset of the dual space. Now if we consider the annihilator of that set, so that would be again that would be a subset of double dual. And then since we know that the double dual can be identified by the vector space because there is an isomorphism between V and V double dash. So somehow we can relate the double annihilator with the vector space itself. So this is what I will start with. So before I start, let us make this observation. So let us start with this observation. If you have any doubt at any point, you can stop me. So let me recall what we did. So we know that if we have a vector, let's say V in the vector space, okay, then we can always talk about we can always define a linear functional on V dash. That means if you remember, we can always find this functional LV, which is from V dash to F, and how it is defined, it is like LV of F goes to F of V, right? So clearly we can say that this is in V double dash. So this we have already seen. So for every vector, we can talk about this. We can always define this linear functional on V dash. So that means for every vector V, we can find an element in the dual space. But then the converse is also true, that if we have a and if we start with an element in the double dual, then we can always find a vector in the vector space V such that linear functional or the element of double dual can be related via this kind of map because of an isomorphism. So let me write this. So we know that we have an isomorphism between V to V double dash, and how it is defined, it is like you send this V to L subscript V. So this is an isomorphism. This is also we have seen, right? So we can basically using this isomorphism, we can identify uh, the space V and its double dual V double dash. Like if there is an element in V, then we can talk about because of this isomorphism, we can talk about the corresponding element in V double dash, and if we have an element in V double dash, we can talk about corresponding element in V using this isomorphism. Okay, so therefore we usually identify V with LV like this, and say that V is the dual space of V dash. So usually what we have, we say that uh, V dash is the dual of V, right? But and similarly we can say V double dash is the dual of V dash. But because of this identity, because of this isomorphism, we can identify V double dash as V. I mean, it's in vague language, and we can say that okay, because for every vector in, so there is an isomorphism between V and V double dash. So we can say that okay, V is the dual of V dash. Okay? So that means the V and V dash, they are like naturally in duality with each other because of this isomorphism. Okay, this is what we can keep in mind, and then we can talk about the following. So let's say we have a, let's talk about the double annihilator. So how do we define? So let us first analyze this. So if I take any, let's say, if I start with a subset in V dash, let's say, okay, since V dash is also a vector space, so I can talk about its annihilator. So what it would be? So annihilator would be a subset of its dual, which is this one, which I can write as V double dual, right? But what is, by definition, what is this E annihilator? So annihilator of V, it is the collection of all linear functional on V dash. That means the collection of all elements in V double dash, such that L of F equal to 0 for all F in E, because E is a subset of V dash. So the elements of E are functionals, linear functionals on V, right? But then, so you don't get confused with this notation. So this is what I'm saying is the equality here, and here it is a double dash means double dual. Now here the left hand, this side here, uh, this quantity here, this is equal to what? Because of this isomorphism, I can write it in this way, that for every L, I know that this L would be of the form L subscript V for some vector V in the vector space capital V, right? Because of this isomorphism, I can write it in this way, L subscript V. It's the same thing, because for every L, I know that there exists a V such that L is equal to L subscript V. So such that, so LV in V double dash such that there exists a V in V such that L is equal to LV. If L is equal to LV, then what would be L of F? It is actually LV of F equal to 0 for all F in, right? And we know that what is LV of F? It is just F of V. So if I rewrite this thing, then you can see that although it's not same, but because of this isomorphism, this set can be identified as this one. So maybe I will not write it as equal, but let's say it's almost equal. So because of this isomorphism, it can be identified. So can you tell me, if I want to write this set as a as a subset of V, how would I write this? Can you, because of this isomorphism, can you rewrite this thing? It's not exactly because here the elements are linear functionals on V dash, and I'm talking about a subset of V. But what I'm saying is that because of this isomorphism, we can somehow relate this set, or we can identify this set with a subset of V. So can you tell me what would be that subset? Just look at this, whatever I have written here. Can you rewrite this thing as a subset of V using this
Ye-
isomorphism?
yes, sir.
Yeah, tell me.
Sir, V belongs to V such that f of V equals to 0 for all f belongs to E.
Yes, exactly. Now you see here, what we did here is the collection of all vectors v in V such that f of v equal to 0 for all f in E, and E is a subset of V dash. Thus you can see that what was this here? This is annihilator of E, right? This, so if you look at here, this is the same thing. So this is equal to this set, and this is equal to this thing. So this is actually annihilator. And now annihilator we have identified as a subset of V because of this isomorphism. So what you can say here that, so this is the observation we are making. Thus if we identify, so if we identify V double dash as V, because both are isomorphic, both are isomorphic. If this is the case, then we can write, then we can write E annihilator as collection of all vectors V in V such that f of V equal to 0 for all f in V. Okay. So if we have a subset of, if we have a subset of dual space, then its annihilator is a subset of V. Okay. So this observation leads us to the following definition. So this is what we can say now. So we write it here. So this observation leads us to the following. That if we now, if I take any subset, let's say W of V, so any subset, then I can talk about its annihilator. So its annihilator would be the collection of all, annihilator is a subset of dual space, so it's a collection of all functionals that on V, that means f belongs to V dash, such that f of W equal to 0 for all W in capital W. This is annihilator. Now, since this is a subset of V dash, so I, when V dash is a vector space, I can talk about its annihilator also. So if I take its annihilator, then what it would be, because of this above observation, we can say that it is a collection of all vectors in V such that f of V equal to 0 for all f in W annihilator, right? So from this, clearly you can say, so from this, so clearly you can say from here that W is always subset of W double annihilator. If we define it in this way, then, right? So this is fine. So is there any problem in defining this double annihilator? Okay, so if there is no issue, then we can prove this result for the annihilator, that let's say if W is a subset of V, W is a subset of V, a subset, and let's say we are talking about finite dimension vector space only. So V is a finite dimension vector space and W is a subset of V. Then span of W, because W double annihilator is always a subspace, that you can verify, because we have seen that, right? We have seen that whether W is a subset or not, its annihilator is always a subspace. W is a subspace or not, W annihilator is always a subspace. Now here I said that W is a subset, so I am starting with a subset, so it may not be a subspace. Then what I can say that this span of W is equal to W double annihilator. So that means it's a when it's a subspace, then you can just say W is equal to W double annihilator, because here I started with a subset. So if I want to say that this is equal to W double annihilator, I will have to make it a subspace. That means the span of W, which is a subspace. So we can say that the span of W is equal to W double annihilator. So let's prove this. So there are two sets. We have to show them equal. So one thing is clear from this, from the above observation. We know that W is always subset of W double annihilator, right? So since from the observation we know that. So let me first write that. Let's say S is the, just to shorten the notation. Let's say S is the span of W. Okay. What is our claim? Our claim is to show that S is equal to W double annihilator. And since S is the span of W, you can verify that this W double annihilator is actually equal to S double annihilator. So annihilator of a set and its span same. This you can verify. So basically we have to show that S is equal to S double annihilator. Now what is clear if from the from this observation, can you say something from here? What can you say from this? So you can say that W is a subset of W double annihilator always because of this above observation. Now
The
because
span
of
of W subset of
W double annihilator, right? So if W is a subset of W double annihilator, then you can say that the span of W is also subset of W double annihilator because W double annihilator is a subspace. So what you can say from here is that, so clearly from the above observation, we can say that, uh, let's say from the observation, S is subset of S double annihilator, right? Because W double annihilator is same as S double annihilator. Now we have to prove the other direction. Okay. Now here, either there are two ways. Either we take an element in S double annihilator and show that it belongs to S, or there is another way. What is that way? So we have already shown one side inclusion. We have to show the other way also, or because we want to show them equal. So one way is that I take an element in S double annihilator and I show that it also belongs to S. That is one way. And there is another way. What is that? Can you suggest something else? I mean, a different way of proving this? The other side. So S is the span of W, so it's a subspace. S double annihilator is also a subspace. Now, can you say something for this? If I show, so V is a finite dimension vector space. S is a subspace of V, so it's a finite dimension. S double annihilator is also finite dimension subspace. So if I show that the dimension of S is equal to dimension of S double annihilator, then I am done. Because we have two subspace, one is a subset of other, and they have the same dimension. So that implies that they are same. Now why the dimensions is same? Uh, Dimension of V, we know what is dimension of V. Dimension of V is whatever is the dimension of V. I can write it as dimension of S plus dimension of S annihilator, right? Since dimension of V, we know that we can always write it in this way. We have proved this result. This is true for every finite dimension vector space and its subspace. Now the same thing I can use for S annihilator also, because S annihilator is a subspace of V dash. Since dimension of V, so V is finite dimension, then we know that V dash is also finite dimension, and dimension of V dash is same as dimension of V. So what we can say similarly, that dimension of V dash is equal to, if I apply the same thing for S annihilator, this dimension of S double annihilator, right? But then from these two, because we know that dimension of V is same as dimension of V dash, from here we can say that dimension of S is equal to dimension of S double annihilator, and this implies that S is equal to, right? So which is same as W double. All right. So this is how we can identify S double annihilator for any given subset S of a vector space. So any doubt so far? Okay, if not, then let me define transpose of a linear transformation. So we know that transpose of a matrix. So let's see how we can relate. So we know that there is a relation between the matrices and the linear transformation. There is a way, right? There is a way to, if we start with a linear transformation, then we can talk about its matrix with respect to some basis. And if we start with a basis, then we can always define a linear transformation for which for some given basis for which the given matrix is the matrix representation of that linear transformation. Right? We have both ways to go from one side to other side. We have seen that. Now for matrices, you know the transpose. You can always interchange like you can always make rows as columns and columns and chains. So you can interchange rows and columns. So that's how you obtain transpose of a matrix. But then can we talk about transpose of a linear transformation also? And if yes, then there should be like transpose of a matrix and transpose of a linear transformation. There should be some relation. So that's what we are trying to see here. Okay. So let's talk about transpose of a linear transformation. So suppose that we have two vector space, let's say V and W. Okay, they are vector space over the same field F. And suppose that we have a linear transformation from V to W. So suppose that this is a linear transformation. Okay, then 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 this T induces a linear transformation. So this T is a mapping from V to W. It's a linear transformation from V to W. Then this T induces a linear transformation from W dash to V dash. So what I'm saying that using this T, you can define a linear transformation from W dash to V dash. How it is? So let's see it here. So what we are given? We are given a linear transformation. Let's say T. Let me use a different color. So we are given a linear transformation T from V to W, right? Now, if suppose I want to define a linear transformation from W dash to V dash. This is what I want to define. Okay. So if I want to define a linear transformation from W dash to V dash, how would I do? I mean, what it should be? I should take a, let's say an element in W dash. So w dash is the linear functional on w. So let's take any linear function on w. Then I should send this to a linear function, let's say f on v, with some rule. Okay, this is what I want to do. So if I take any g, so g is a linear functional on w. So what is linear function on w means? G would be here. It's a map from w to f, right? Now using this g, now t and g, I can relate. So using this t, I can relate. I can define a linear functional on v. Can you tell me what we can do here if I want to define a linear functional on v? So I want to define a linear functional on v. Now using this information, can I do that?
Decompose G.
Yeah. So if we, so one usual way is that we take the composition. So if I take the composition, then what it would be? It would be, let's say f. Let us call this f, which is g composition with t. So g composition with t. This is how I can relate. I can define a function from v to f using this. And since t and g both are linear, t is a linear transformation, g is a linear functional, so they are both are linear. So you can easily check that this f, the composition is also linear. So we can always define a linear function. So for every element g here, we can find a f, which is actually g composition with t. So now you can say that then this t induces this t uh, induces a linear transformation from w dash to v dash as follows. So how it does? So if I take any element g in w dash, then using this g, I can define this f, which is basically g composition with t, right? Or you can say that is f is a function. So now you can see from here that this f is a function from v to f. So you can say that it is f of v is equal to g composition t of v. This is what I'm talking about. Okay. So now using this information, we can define this linear transformation. Let us call this t superscript small t from w dash to v dash. And how it is defined? You send any g to g of t, or g not t, that means g composition with t. Okay. So this is what you can do, right? So G composition with T, it's a linear functional on V. So you can also write the same thing as follows, because it's a linear function on V. So it will act on vectors or elements of V. So you can write it in this. Now this T superscript T, this you can see that this is linear. This is linear because G and T both are linear, so their composition is again linear. So this T superscript T is also linear. And not only this, the way you have defined this using this composition, this is a unique way to do this, or this is a unique, you can say the transformation, linear transformation from W dash to V dash, such that it is defined in this way. Okay. So what I'm saying is that why this is unique? Because the way it is defined. So it's defined by using the composition. So if you suppose that there is another map, let's say S from W dash to V dash, such that it sends G to F using G composition S. But then the composition is unique with a function. So if you have like this, what I'm saying is that if you have G composition T is equal to G composition S, okay? Oh, sorry, G composition T. So it's a unique way. Actually, you cannot define another map using the same composition, because T is a given map, and you want to relate every functional on W with using this decomposition. So there is only this way to define this. There is no way to like define a different one or another one. So for any T linear map from or linear transformation from V to W, you can say there exists a unique linear transformation, let's say T superscript T, this is the notation we are using, from W dash to V dash, such that T superscript T G of V is equal to G composition T of V. Okay. Since it's a unique way to define, we can give a name to this transformation here, which is induced by T. We call it the transpose of T. Okay, so this thing is called the transpose of. Okay. So for every linear transformation T, we can talk about its transpose, and it is defined in this way. It is defined by using this uh, composition. Okay. Now for this transpose, we can relate the transpose. So transpose uh, is a uh, is a linear transformation from W dash to V dash. So we can basically, so it's a if we take a null space of transpose of T or range space of transpose of T, then it is either a subset of the dual space of W, or the range space is a subset of a dual space of V, right? So there is a way, or there is a result that relates the null space of transpose of T and range space of transpose of T with the with the range and null space of T using their annihilator. So what I'm saying is the following. So if we have V and W two vector space, let's say, over F. So while defining this, if you can see here, while defining this transpose, I haven't used the dimension of V and W. So this way we can define for any vector space V and W, whether they are finite dimension or infinite dimension, we can talk about this transpose this way. Okay. So what I'm saying here in the next result is that if suppose we have two vector space V and W over the same field I, and suppose we are given a linear transformation from V to W. This is a linear transformation. Okay, then you can always show that you can prove that null space of the transpose of T. So null space of transpose of T, it's a subspace of W dash, because transpose of T, if you look at here, it's a linear transformation from W dash to V dash. So null space of this would be a subspace of W dash here, right? So it would be a subspace of W dash. So now null space of T transpose, you can say, or you can prove that this is equal to uh, range space of T annihilate. So this, how to remember this? So you can actually prove this, but there is a way. I mean, you can easily remember this thing, because null space of T transpose, it would be a subspace of W dash. And now you want to say that this subspace is equal to some subspace, so that subspace should also be a subspace of W dash. Now we know that there is a subspace of W dash which we can find using this T. So what would be range of T? If you look at range of T is a subspace of W. Now if I take the annihilator of that range of T, that would be a subspace of W dash, right? So that way you can say that null space of T transpose is equal to range of T. Now you can, we will prove this. This is something which is true for any given vector space V and W. But if in addition to that, if W is of finite dimension, in addition to that, if W is of finite dimension, then let's say, let me write this here. If V and W, let's say V and W are of finite dimension, then, so this is, let's say this is first one, then we have, we can show that rank of T is same as rank of T transpose. Not only that, we can prove that range of T transpose is equal to null space of T annihilate. Okay, so the proof is not difficult, it's very easy. So let's prove the first one. Okay, we have to show that null space of T transpose is equal to range space of T annihilator. Okay, so we have to prove that these two sets are equal. So we'll follow the usual way. We'll show that one is contained in other, and the same way the other side is also true. Okay, so you tell me now what to do here. So I'll take an element, let's say G, in the null space of T transpose. Okay, now you tell me from here how to show that G belongs to the range space of T. Just follow the definition. So if G belongs to null space of T transpose, then what? So we are proving the
T
first one.
transpose of G equals to 0.
So you are saying that from here you can say that this implies T transpose G is equal to 0, right? So you can say this way. Then so what is T transpose?
G
Yes.
of T transpose is 0.
So that means G of T, or G of T transpose means you are saying that this composition, right?
No, sir. Yes, sir. Just G of T.
G not T. This is 0, right? Because this is how we have defined this transpose. But then what? What you can say from here? Keep in mind what we want. We want to show that G belongs to the annihilator of range of T. So if G not T, that means G composition T. If you go back and see, what is this? This is a function from V to F, right? So if I'm saying this function is 0, that means its value at every point is 0. So what you can say from here, that G PV equal to 0, or you can
Yes.
say this
For
way,
V is equals to 0.
right? So you can say this thing is 0, right? But what is the meaning of this? This is true for all V in V. So can you say from here that G belongs to the range of T annihilator? What can we say from here? So this thing is true for all V. Now what can you say from here? Can we say that from here that G belongs to range of T any letter?
Yes, sir, but TV can be 0 also.
So what? So 0 also belongs to the range space, no?
So then V belongs to that null space of T.
No, no. So what I'm saying, if you can say that G of TV equal to 0 for V, what is this TV? So what is the range of T? Let us say range of T you write this way, no? This is another
So
way
yes,
to
sir.
say. Now if
Yes.
this is, you can say that for every V, G of TV is 0, then can you say that G belongs to the
G is
range of T any
annihilator
letter?
of. Yes, sir.
Yes. So then where is the confusion? So from here you can say that G belongs to range of T any letter. Okay. So this is one way. Now first check whether the other direction is also true. Now let's say if I take, let's say here, if I take G belongs to range of T any letter, then what does it mean? It means that G of TV equal to 0 by definition for all V if G belong to range of T any letter, right? Is it true? From here to here, can I go from here to here? Can I
Y-
say that if G
Yes,
belongs
sir.
to range of T? So this is also true. Now, what about the previous step? So can I say from here to the step above, if GTV equal to 0 for all V, can I say that G composition with T equal to 0?
Yes, sir.
Yes. And but then it's the same thing as saying that T transpose G is 0 because G naught T equal to actually T transpose G. But if this is the case, then you can say that G belongs to null of T. So what I'm saying is that the other direction is also true in this case. And therefore you can say, so this implies you can say that null of T transpose is same as range of T annihilator. So we know where we have used dimension. So it's true for every vector space we end up. Now we are given to prove two and second and third, we have to use the dimension. So because they are given finite dimensional now, because we want to talk about rank of T and rank of T transpose. So here, let's prove second. So second, we have to prove that rank of T is same as rank of T transpose, assuming that uh, V and W are finite dimensional. Now, can we do that? So this is straightforward base actually. So how to do that? So let me write this to save the time. Dimension of range of T, which is actually the rank, and dimension of range of T annihilator. See, we want to relate the dimension of range of T and range of T transpose, right? So now you look at here, what I can do from here. This is equal to dimension of, can you tell me what would be the dimension of this? This is equal to dimension of, so it's like dimension
V.
of W plus dimension of, it's dimension of V or dimension of W?
So W,
Range of
sir.
T
W,
is
sir.
W, sir.
W,
W,
the
sir.
dimension of W. Okay. So from here you can say that the range of T or the rank dimension of range of T is actually equal to dimension of W minus dimension of range of T annihilator, right? But then from above result, what it is? is the same as dimension of W minus dimension of range of T annihilator is same as null of T transpose,
Null. Yes.
right? So it's the null of T transpose. But then what? Now what it is? Can I say that it is the dimension of range of T transpose? Can I apply rank nullity here again for T transpose? So T transpose is a map from W dash to V dash. V and W are finite dimensions, so W dash and V dash are also finite dimension. So we can talk about rank nullity. We can apply rank nullity for T transpose also. But then what would be the rank nullity? Dimension of W dash is equal to dimension of range of T transpose plus dimension of null of T transpose. But dimension of W dash is same as dimension of W. So dimension of W minus dimension of null of T transpose. Can I say that it is equal to dimension of range of T transpose?
Yes, sir.
Yes. So it's because of rank nullity, you can say dimension of range of T transpose. Why? Because dimension of W is same as dimension of W dash. And you are done. So this is also straightforward. Now let us prove the third one. So what is third? Let me write here. We have to show that range of T transpose is equal to null of T annihilator. This is what we have to prove. Okay, this is our claim. So what I will do, I'll show that one is contained in other, and to show the other side containment, I will show that these two spaces have the same dimension. That would be easy to show. Okay. So let us show that range of T transpose is contained in null of T annihilator. So use the same thing. Let us take an element in range of T transpose. So if I take an element of in the range of T transpose, so element would be of the form. So T transpose. Let me again recall. It's a linear transformation from W dash to V dash. So if I take an element in the range of T transpose, that means it would be an element of V dash, right? So let us take an element in the range of T transpose. So let's say F. F belong to range of T transpose. So it's a linear functional on V. So F is a linear functional on V. It's an element of range of T transpose. So what can we say from here? We have to show that F belong to null of T annihilator. So what can we say from here? Just use the fact that F belong to range of T transpose. What can we say from here? If F belong to range of T transpose, then what we can say? If F belong to range of T transpose, then we know that it will have a pre-image. So there exists a G in W dash
Such
such
that
that
T transpose of G equals to F.
T transpose G equal to F, right? But then we know, so T transpose of G equal to F. But then these two are functions, right? T transpose G. So if you recall, T transpose G is what? It's a G composition with T is equal to F. And F is a linear functional on V. So, and you are saying these two things are same, that means their function value is same. So this is same for all V belongs to V, because F is a linear functional on V. Now, if you want to show that F belong, what you have to show? We want to show that F belong to the null of T annihilator. That means I have to show that if I show that f of v is 0 for all v in the null of T, then I am done. But can you say from here that f v equal to 0 for all v in the null of T? Can you say from here? So what I'm saying, up to this is fine, right? So this is true because f belong to range of T transpose. Now what I'm saying, now if v belong to null of T, if v belong to null of T, then what does it mean? Can we say that
T
f of
of
v
v
equal to
equals to
0?
0.
From here we can say T of v equal to 0, but then does it imply that f of v equal to 0? Because f of v is equal to actually g T of v. So if T of v is 0, then we have this, right? But can you say that z0 is 0?
Yes, sir. G is a linear functional, then g of 0 equals to 0.
Right. So it's the easy thing. So if we have a element or if we have a vector in the null space of T, then this implies that f of v equal to 0. So what does it mean? This is true for all vectors in the null space of T. So this implies that f belong to null of T any letter, right? This is only one way. So because of this, we can say that if I take any element in the range of T transpose, sorry, if I take any element in the range of T transpose, then that element f belongs to the null of T any letter. So we have shown one side containment. So this implies that range of T transpose is contained in null of T any letter. So for the other direction, I will show that both these spaces have the same dimension, and then they are same. So for converse, what I will do, or for the other direction, I will show that they have the same dimension. So again, use the same rank nullity and the other result. So we have two results for the dimension. One is the rank nullity theorem, and the other one is dimension of W plus dimension of W annihilator is equal to the dimension of the space. So here, let us see what it is. So dimension of null of T plus dimension of null of T annihilator is equal to dimension of
V.
V. So what you can say from here, that dimension of null of T annihilator is equal to dimension of V minus dimension of null of T. But what is the right hand side? It's equal to dimension of range of T because of the
Range of
rank
T.
nullity theorem. But then what it is? We have proved in the previous result that the dimension of range of T is
Range of
same as
T
dimension,
transpose.
right? So dimension of range of T transpose. So therefore, they have the same dimension. So this implies that range of T transpose is same as null of T annihilator. And we are done. Okay. So this is not difficult to prove. This is very easy. But using this result, we will prove a very interesting result for you have heard about. You might have heard about row space and column space of a matrix, and then you can talk about column rank and row rank. I'll just introduce this terminology again, and then one can prove that the row rank is same as the column rank. So using this result, you can easily prove that. I will show how. But before that, let me give you an exercise. As I mentioned at the beginning, before starting this transpose of a linear transformation, that we know what is the transpose of a matrix, And we also know that there is a way to go from set of linear transformation to set of matrices. There is a relation between these two. We can always define for a linear transformation, we can always talk about its matrix representation. And if we are given a matrix, we can always define a linear transformation for which the given matrix is the matrix representation with respect to some basis. Okay. Now, since we know transpose of a matrix, now we also know transpose of a linear transformation. We want to see how these two things are related. So of course, if you want to relate the transpose of a linear transformation and transpose of a matrix, you for the linear transformation you will have to pick its matrix representation. Then only you can relate to two matrices. Now, can you guess, like just vague guess, what would be, so if I given, so let's say if I'm given uh, a linear transformation T, and with respect to some basis, let's say I have its matrix representation also. Let us call this A. So if I have a linear transformation T and I have its matrix representation, which is, let's say, A. Now, can you guess what could be the matrix representation of T transpose? Remember, T transpose is a linear transformation from W dash to V dash. But at least just to guess something, first thing is that I need, so T is a map from V to W, and T transpose, I know that it's a map from W dash to V dash. So for V and W, I have basis B and B dash. So first I need to figure out some basis for W dash and V dash first. And then if somehow I am able to find these two bases, let's say B tilde and B tilde dash, one for W dash, one for V dash, then I can talk about its matrix representation with respect to these. Then what can I expect? Can you guess something that this matrix representation would be this? So if
A transpose, sir.
A transpose, so this is our guess. So if we want to relate these two things, so the guess is that, okay, can we say that the matrix representation of T transpose is actually the transpose of matrix representation of T? That is what we want to see. Answer is yes, provided you choose these bases appropriately. Now, can you also guess what basis I should choose for this W dash and V dash? I am given basis B and B dash. I mean, of course, we will see the details, but just to guess, because I am given basis for B, V, and W. Here I am given. I need a basis for W dash and V dash. Can I somehow use these bases to find W dash, basis for W dash and V dash?
So by dual basis.
Take the dual basis. You know how to find a dual basis, right? So it's a dual space of
Yes, sir.
W. So you find a dual basis for B, B dash, which would be B tilde, and then you find a basis for B, which would be B tilde dash. You find their dual basis, and with respect to dual basis, you see what would be the matrix representation of T transpose. And it turns out that this matrix representation is actually equal to the transpose of matrix of T. So this is in fact true. And as you can see that you can guess this, we are given a linear transformation. We want to see how we can relate the matrix representation of T transpose. But before we talk about matrix representation of T transpose, we need two things, these bases. And these bases should be, we want to relate these two things. So these bases should depend on the given basis. And there is a way, which is the dual basis, to find basis. And then we can say that this is true. The matrix of T transpose is same as the transpose of matrix of T. So this, let me write properly, and I give this you as an exercise. You can also find this in any textbook. Therefore, I don't want to do it here. but I want to tell you the result. So let me give you this as an exercise. So let T is a linear transformation from V to W. It's a linear transformation. Okay. And suppose we have basis. So um, let's say BV. This is a basis for V, and let's say PW is a basis for W. Okay. And also you want to talk about T transpose, right? So you need basis for W dash and V dash also. They're dual space. So you take the dual basis. So dual basis of BV is BV dash, and let's say of BW is BW dash. So these are the dual bases. Then you can show that the matrix representation of T transpose with respect to BW dash and BV dash is same as the transpose of matrix of T with respect to BV and BW. Okay, so this you can prove. Now if suppose I want to find, so in case of, let's say if we have a uh, let's say we have a let's say if we have a we have a let's say we have a Rn to Rm, some map we have, and if we take the standard basis for these and these, then their dual would also be standard. So if I take the, you can verify that if I, so if E1 to En, this is a basis for Rn, and let's say E1 to En, these are the standard basis for Rn. Then if I take the dual basis of BW, it is actually same as E1 to En. And similarly for this also it would be same as E1 to En, BV dash. In this case, you can see that the transpose of T, the matrix representation of transpose of T with respect to this basis is same as matrix of T transpose. It's because of this result only, but in this case, it is easy to see this because the dual basis is same as the given standard basis. Anyway, so this you can verify. You can also verify that this is true only if you take the dual basis of the given basis. If you just take arbitrary basis for W dash and V dash, then this result may not be or need not be true. Okay, so let us take an take a as an application of this result. Let us prove the following. So what is the problem? So I'll write this as a problem. So the problem is to show the following. Suppose that we have a matrix, let's say M cross N matrix over F. F is either R or C. Okay. Then we have to show that the row rank of A is same as the column rank of A. You might have heard about this result. You might have also proved this using some other way, but using the exercise or the previous result, we can actually prove this in a much easier way. So what is row rank? Let me again recall this. Row rank means the dimension of the row space of A. Row space means the space spanned by rows of A. And similarly, the column rank is the dimension of the column space. So what is column space? Is the space spanned by columns of A. So this is column space of A. Okay. So I assume that you know what is row space and column space. So what we are trying to prove here is that the range space of A and the column space of A and the row space of A, they have the same dimension. Now this we can prove by using the previous result. So how to prove this? So I know that I am given a matrix A, so I can define a linear transformation T from Fn to Fm such that the matrix of T with respect to the standard basis is the given matrix A. Right? You know how to do that. So can you tell me how to define this map Fn to Fm such that matrix of T with respect to the standard basis is the given matrix? Can you tell me how to define this transformation T here? We have done this.
So V1, V2 basis Vn, V1, V2 total Vn. Then T of V I equals to summation over
So basically, yeah, summation of
uh, coefficient AI is
yeah.
a
So
Vi.
right. So it's actually the same idea, but I can write it in this way also. If I take let's say x here, so I assume that x is of the form x1 to xn. So let us call this x. I send this tx to ax, multiplication of a with x. Then this is actually you can see it's exactly the same map as you are saying, but I have written it in compact form. For this map, if you take the standard basis for Fn and Fm, so let's say if I take B for Fn, so let's say E1 to En, it's the standard basis for let's say standard basis for Fn, and let's say B tilde, the B tilde is E1 to En. This is a standard basis for Fm. Then you can verify that the matrix of T with respect to this B and B tilde is actually A. This you can verify. Now also, not only this, if I write this A, suppose that the columns of A are of this form. So if I write A as column wise, let's say A1, A2, so A is of size m cross n, so it will have n columns. So let's say these are the columns. So these are the columns of A. So I have written A column wise. Then you can verify that this, when I say AX, it is same as saying that x1 A1 plus x2 A2 and so on up to xn AN. It's the same thing. So what I've done, AX is the multiplication of A and X, but I have written it in this column wise multiplication. So it's the same thing. When you multiply and when you equate these two sides, you will see that they are the same. Where x1 and xn, x1 to xn, they are the components of x. So from here, since T is linear, so you can verify that this map is linear. So this T, so if you do it, then this T is linear. And what is the column space of T, or column space of A, or let's say range space of T? What is the range of T here? Range of T is actually, if you look at here, A1, A2 and up to AN, they are the columns of A. And this x1, x2, they are the scalars, right? They belong to F. So this range of T is basically the column space of A. It's the span of columns of A, right? So this range of T is basically the column space of A. So if range of T is equal to column space of A, so you can clearly say that from here that the dimension of range of T, which is actually the rank of T, which is same as dimension of column space of A, which is the column rank of A. Okay? Because they are the same, so they will have the same dimension. So dimension of range is called rank, and dimension of column space is called column rank. So this is fine. There is nothing special so far. Now I want to use the previous result because I want to show that the dimension of column space is same as the dimension of row space. And how I can relate this thing, dimension of column space I already know, and I know that the dimension of row space is same as the dimension of column space of A transpose. So there is a relation between the columns of A transpose and the rows of A. They are the same. So the column space of A transpose would be the row space of A. And I want to use this fact. So what I can do here, if I take the dual basis of B and B tilde, it is same as so B dash, let's say B dash will be the dual of B tilde. So it would be E1 to En, sorry, B, and B tilde dash, this is E1 to En. These are the dual bases of B and B tilde. Okay. Then the matrix of T transpose, because of this result, you know that what would be the matrix of T transpose with respect to this dual basis here. This is actually A transpose, right? So what you can say, if you use the same thing for as you did for this A, if you do the same thing for A transpose, then what you can conclude from here, you know that you can say that rank of T transpose. So you can see that whatever we have proved here, that rank of T is same as column rank of A. Whatever we have proved for any matrix A. Now if I replace A with A transpose, then T would be replaced by T transpose. So the rank of A transpose, we can say, if we follow the same thing. So by the same reason, let me write here. So by the same reason, same reasons, we can say that column rank of A transpose is same as rank of T transpose. But column rank of A transpose, that means the dimension of the column space of A transpose. But the column space of A transpose is same as the row space of row space of A. So the column rank of A transpose would be same as row rank of A. So what we have done here, so we have proved that rank of T is equal to column rank of A, and row rank of A is equal to rank of T transpose. But we know that rank of T and rank of T transpose are same. We have proved this, right? So rank of T and rank of T transpose are same. So this implies that column rank and row rank are same. So thus this implies that row rank of A, which is same as rank of T transpose, but rank of T transpose is equal to rank of T, and rank of T is equal to column rank of A. So this is equal to column rank of A, because rank of T is same as rank of T transpose. So this is another way to prove that for a given matrix, row space and column space have the same dimension. All right. So with this, what we will do the next, we will. So usually we define eigenvalue, eigenvectors first, or we study eigenvalues first, and then we talk about inner product. But I will do it in the other direction. I will first talk about inner product space. Once we have some knowledge of inner product, then I will define eigenvalue, eigenvector, because I want to use some of the terminology from inner product space to eigenvalue eigenvectors. So so far we are developing results for linear transformation as well as for matrices. So we are trying to connect results for matrices as well as for linear transformation. So whatever result we have for linear transformation, we are trying to connect it with the corresponding result in matrices, and the other direction also we are trying to see that. After some point, after introducing this linear transformation, this inner product and basic definition of eigenvalue eigenvectors, I will completely focus on I will completely switch um, to matrices, because then doing things for matrices. So once we have basic knowledge of this for both the things, for linear transformation and for matrices, I will switch to matrices mostly, because talking about matrices or proving results for matrices is much easier than the linear transformation. But whenever we need to see, we will talk about the corresponding result for linear transformation. But I'll mainly focus on matrices, but the corresponding results we will also see, or we will also discuss for linear transformation, that what would be the corresponding result for linear transformation. But the main focus would be on matrices, so that we can cover some of the basic things for matrices also, and we can talk about okay how to like uh, practically deal with large matrices and this thing. By the way, at the beginning of this course, I also mentioned that we may we will discuss about application of the topics which we are learning here. But so far, I have not given any lecture on the application part, because we are going very slow. I'm taking more time. I'm stretching every topic a bit too much, so I did not get much time. But I'll try to take at least one or two lectures completely devoted to. I'll completely devote one or two lectures to application part. Like some of the application which are very useful. For example, uh, so I got 10 minutes, so I can tell you that it's very important also to know whether what are the applications we have in the real life of the topics which we are learning here. So you can see that as I mentioned earlier also in my first lecture, there are linear algebra is everywhere, because whatever we do, or whatever system, whatever thing which we can control, there is a linear algebra in the background. So whatever, so if you want to switch on the AC, if you want to switch off the fan, if you want to switch on the TV, whatever system which you can control, there is a linear algebra in the background. There is, wherever there is a control system, there is a linear algebra in the background. But I'll I'll give some precise application of some of the topics. For example, WhatsApp we use, right? We all of us we all are using WhatsApp in our day-to-day life. So but how it is working? Have you ever thought about how WhatsApp works? It's actually linear algebra in the background. I'll tell you. I'll give you how it actually works. I'll explain that. And we all use Google, right? So Google, we whatever we need, we just search, we just type on Google search engine, and it will give us the result. But again, have you ever thought about how it works? So how it is possible that whatever we type, at least some result will pop up. But how it is possible? I mean, how, what is the algorithm? What logic Google uses to do that? It is actually eigenvalue eigenvectors. So I will give some more details on how actually it works. So I'll take one or two lectures on, at least to cover basic application part, so that you also realize that whatever topics we are learning here they are useful in our real life. Of course, we will cover the theoretical part so that you can use these things for your higher studies. But you should also know that for our real life, in our real life world, these things have a lot of application and they are useful. So if somebody asks you, okay, you are doing this, but what is the use of this thing, and you can immediately say, okay, it's everywhere, it's here, it's there, it's in your computer, it's on laptop. And you know what, whatever graphics we see on computer screen, it is linear transformation. So you can ask, what is the use of linear transformation? Actually, it is whatever graphics you are able to see, whatever picture you see, whatever like editing you do with your picture, like you move one picture from one place to other place, or you zoom in or you zoom out, or you expand like a given picture, or whatever you do, it is actually linear transformation, right? You rotate a picture, you reflect a picture, these are linear transformation. You see, we have a, if I take a picture, like if I go outside and if I take a picture of a building is a three-dimension object, right? It's a three-dimension object. And but when I see this picture on my computer screen is a two-dimension object. So how to like see the three-dimension object outside on our computer screen, which is a two-dimension object? So it's using a projection. So three-dimension object is projected onto a two-dimension plane, and this is how we see the picture. So when this projection is used, the projection is a linear transformation. And there are many kind of projection like oblique, orthogonal. There are many kind of projections there, but it's a linear transformation. So that's what I'm saying, that whatever we do in most of the things which we can control, it's it's linear algebra in the background. So in our Google search engine, in our WhatsApp, in our computer graphics, in our computer control systems, whatever we can control in our surrounding, it's a linear algebra in the back. So I will discuss more about these applications. I will specifically take one or two depending on how much time we have. I'll take two lectures on mostly on application part, where I will give more details on how it actually works, like how I'll take two lectures, one probably on Google search engine, how to tell you that how it works, and one on maybe on WhatsApp or computer graphics, how this linear transformation or these things are used in WhatsApp messaging or computer graphics. Okay, so with this we can stop here. In today's tutorial class at 2 o'clock, I will discuss either me or the tutors, but I would be there. They would be discussing your exam problems. Okay, you can also discuss the problems from the last tutorial sheet, but the mostly we will first discuss these exam problems, and then still if you have doubts, and if you feel like your copy has not been corrected properly, or it has something has been missed by us, so then you can raise that issue on Gradescope. We will address your issue. All right, with this we can stop now. If you have any doubt, you can ask. We still have 3 minutes.
Sir, can you arrange today's tutorial class from 2:15?
2:15.
Yes, sir.
And why?
Sir, today we have minor of real analysis till 1:50 p.m.
Oh, I see, 1:50. Okay, so we can do it 2:15, no problem. Is it
Okay, sir.
okay?
Thank you, sir. Thank you, sir.
Yeah. Okay, fine. Any other thing? Okay, so then we can stop here, and I'll see you in the tutorial class.